Dear students, I welcome you for the today's lecture related to the revision of condensation and the numericals associated with the condensation process. Yesterday we have seen the basic equation for a vertical plate condensation over a vertical plate where the force balance and the mass balance of the liquid which is taken, then the a vertical plate which is having the x direction in the vertical and y direction in the horizontal x direction. So y is your thickness of the liquid film which is forming over this thick plate, and at b, that is the width of this plate. Then the viscous forces which are due to the shear stresses mu du upon dy, then the change in the shear stresses in display, that is differential of this shear stress, and so the viscous shear stresses at y plus dy will be the summation of this two, and this is being opposed by the gravitational force. The fluid which is getting moving from top to bottom, it is having the resistance of the shear forces, fluid which is moving in the downward direction, and it is opposed by this gravitational force. So gravitational force is more predominating. So equating the gravitational forces, net and the shear force, and on simplification and integration you will get the equation related to the velocity, then the mean flow velocity of the liquid film at a distance x is a vertical distance, so that comes as the rho g delta square upon 3 mu. From there one can calculate the mass flow rate, that is mass flow rate is equal to velocity into the area into the density. You get GB rho square delta cube upon 3 mu. Then the heat flux, that is the heat flow rate into the film, which is equal to the energy released due to the condensation. So energy released due to the condensation, that means your latent heat that is released. So this released latent heat, the amount of release of this latent heat by the condensing vapor is m lambda. So we are considering this as a small volume, and that is why dm into lambda that is there, and this has to be equated with the dq. Then the Nusselts assume that the heat flow is by conduction through the film. So that is to be equated with the Ka delta T upon delta X. And after simplification, you get the value of delta as 4K mu T saturated minus Ts into the X upon rho square G lambda raised to the 1/4. This film thickness increases as the fourth root of a distance. Then the heat transfer coefficient, which is calculated by equating the Hx Ha delta T, that is Ha delta T, with the conduction equation, conduction through the liquid film. So Hx you get the K upon delta. So the average heat transfer coefficient, that is finally you will get as K cube rho square G lambda upon 4 mu x into bracket T saturated minus Ts raised to the 0.25. So then the average that finally comes as the 0.943 raised to, and the bracket, all these are the constants. Thermal conductivity is for material, thermal conductivity, density, latent heat, viscosity, all are constant. Only at what distance and what is the temperature difference, that is to be noted. So your heat transfer coefficient that decreases with the plate thickness, with the plate height, and the film thickness increases with the increase in the plate height. Film thickness increases with the increase in the plate height. Generally it is 20% excess, so the value of this constant is replaced with 1.13. Now coming to the different situations which arises in the condensation process, that is the horizontal tubes can be used. So at that time your this constant that changes to 0.725 and L that is replaced with the outer diameter. Then it's a vertical band, एक के नीचे एक ट्यूब है. Then vertical band of horizontal tubes with end tubes directly placed one over the another. एक के ऊपर दूसरी, दूसरी के ऊपर तीसरी, like this. So you have to count the end tubes. So this equation that is modified with the n into d0, where n, for example, if the 100 tubes in square array that is there, square array that means 10 horizontal and 10 vertical. So vertical 10 are there and this n is taken as the 10. So these are the different formulas that will be there. So considering the different numericals, let us see the first numerical. A vertical cooling fin approximating a flat plate 40 centimeters in height is exposed to the steam at the atmospheric pressure. If the surface of the fin is held at 90 degrees Celsius, make the calculations for the following parameters, that is the film thickness, overall heat transfer coefficient, and the heat transfer rate and condensation mass flow rate. Whatever the four equations we have studied, we have to calculate them. Now this is a vertical plate with the cooling at 90 degrees Celsius that is there, and plate width that is 40 centimeter. The different physical parameters like lambda, density, thermal conductivity, and the viscosity, they have been provided. Then the film thickness at a distance x from the top, that is we are having the formula K mu into T saturated minus Ts upon rho square G into lambda into the x raised to 0.25. For substituting, for K is your constant thermal conductivity, mu is viscosity, then T saturated, it's a steam, therefore 100 degrees Celsius is steam temperature and wall temperature is 90 degrees Celsius upon the density, then gravity and the lambda. So for x that is equal to 0.4 meter, that is what the approximating a flat plate of 40 centimeter in height that is mentioned, 40 centimeter height that is mentioned. So we are calculating this at the bottommost part, maximum thickness, film thickness. So finally you will get the maximum film thickness as 0.1135 millimeters. Then the value of heat transfer coefficient, that is 4 upon 3 K by delta. So K thermal conductivity it is provided and delta we have already calculated here. So that comes as 9066 watt per meter square Kelvin. Now it is assumption that if it is 1.5 20% excess. The actual values that comes as the 20% excess. So it is multiplied by 1.2 and you will get this value. Then heat transfer rate, that is Q, which is equal to HA into bracket T saturated minus Ts. So H, we can calculate the Q with the calculated value and Q with the 20% excess. So first Q with the calculated value and this area, that is 0.4 per meter length, per meter width, that is taken into account. So this comes out to the 36,323 watts. And if it is 1087, then it comes as the 20% excess to that. So the steam condensation rate, that is the heat transfer rate upon the lambda, that is what the steam is getting condensed. So this is 43,588 divided by lambda, that is going to give you 0.193 kgs per second. The next example, the outer surface of a vertical plate which is of length 1.25 meter and outer diameter 50 millimeter, that is exposed to a saturated steam at atmospheric pressure. So it's the outer surface of a vertical tube of length 1.25 meter and the outer diameter is 50 millimeter, exposed to a saturated steam. That means on the outer surface of a tube, the steam is getting condensed. So it's a vertical tube. If the tube surface is maintained at 80 degrees Celsius by flowing of the cooling water through it, that means the tube's water is flowing and which is at a 80 degrees Celsius. Determine the rate of heat transfer to the coolant and the rate at which the steam is condensed at the tube surface in a film form. If the tube is held horizontal position, what will be any change in the mass condensate? If S, find the value. So first we have to consider this vertical plate, vertical tubes. So a slight modification in the formula, that is your vertical tube, that will be there. So the steam condensing on a vertical tube, you are having 0.943 into K cube rho square G lambda upon mu L into T saturated minus the Ts raised to the 0.25. So this figure showing that the 50 millimeter outer diameter, inside temperature is 80 degrees Celsius, outside temperature is 100 degrees Celsius, steam vapors, steam that is there. So H, that comes as the 5446 watts per meter square Kelvin. This is for the vertical, and the heat transfer rate, that is Q, which is equal to HA delta T. So this H into the area, that is the surface area of the tube. This is the diameter of the tube and this is the length of the tube. So this is what is surface area on which the condensation that is taking place. And the temperature difference of 100, that is the steam, and the inside temperature is 80 degrees Celsius. So steam condensate rate M, which is equal to Q upon lambda, that comes in the kgs per second, 8.7 into 10 to the power minus 3. Then the second part, that is related, if the tube is held horizontal position, what will be the any change in the mass of condensate? So we have to use the horizontal position, and the tube, when it's a horizontal, then your constant that becomes 0.725 and your D becomes your outer diameter. So H horizontal, H in the vertical direction. So H in this vertical direction, you are knowing this value and comparing those two. So you will get the H in the horizontal, that comes as the 8707. That means for a vertical, you get the less heat transfer coefficient. For horizontal tubes, you get a higher heat transfer coefficients. The surface area, even though it is same, but the vapors which comes in contact vertically and horizontally, there is a difference in the geometry. So that difference of the vertical tubes and the horizontal tubes makes a difference in the heat transfer coefficient. So for vertical tubes, you get a less heat transfer coefficient. Then QH, that is in horizontal condition, you get the 34,175. For this Q, that comes as the 19,000. Then for this flow rate, 8.7 into 10 to the power minus 3. Here it comes to the 14.95 mass flow rate. So your heat transfer coefficient increases, amount of heat transfer, that is also increases, and the mass flow rate which is getting condensed, that is also increasing. In the next problem, the 100 tubes of 12.5 millimeter outside diameter are arranged horizontally in a square array and are exposed to the steam. Estimate the mass rate of the steam condensation per meter length if the tube wall temperature is 98 degrees Celsius. Again, the physical properties that is given, steam temperature which is 100 degrees Celsius. If there are the 100 tubes and arranged horizontally in a square array. Square array, that means 10 by 10 tubes that is going to arrange. So the N, that becomes your 10 vertical tubes, and DO, that is the outside diameter of the tube, which is 12 mm, and these are your horizontal tubes. So your formula is 0.725 into K cube rho square G into lambda upon NDO into mu into the delta T. The surface area N into pi do into L. N, that is your number of tubes in vertical direction. So total heat transfer rate, that is HA delta T. So H, that comes as 12,721. Area, that is 3.99 into the delta T of 2 degrees, 100 degrees and 98 degrees. The temperature maintained is 98 degrees. So mass flow rate, that is Q upon lambda, which is going to give 162 kgs per hour, or you can say 0.45 kgs per second. The next example, that is saturated steam at 80 degrees Celsius condenses on the outside of a horizontal tube, 100 millimeter OD and length L. The tube wall is maintained at 70 degrees Celsius. When the tube was kept vertical, it was found that the rate of condensation was same as before. Find the new tube length L and the rate of condensation per hour. The saturated steam, which is at 80 degrees Celsius, condenses on the outside of a horizontal tube. The tube wall, that is maintained at 70 degrees Celsius. When the tube was kept vertical, what was the rate of condensation? Now initially it was horizontal and you are making it a vertical. So you need basic formulas of the horizontal and the vertical. When it's a horizontal, it is 0.725 and this is DO. When it's a vertical, that is 0.943 into the L, vertical length that will be counted. So comparing these two, and you will get L raised to 4 and DO raised to 4, and rest of the things they are constant. So the ratio of this, that comes as the 0.92 meters. That is the length. Then for vertical tubes, using the basic formula, that is K cube rho square G into the lambda upon mu L into delta T. So the H, that comes as the 10,000. So Q, that is coming as 9,146. Mass flow rate, that is coming as 14.31 kgs per hour. Now, in addition to these formulas, also we have discussed some formulas. Then there is a density correction that is also added in some books. So this is getting modified as, instead of writing the rho square, it becomes rho into bracket rho of liquid minus rho of vapors. So this rho of liquid that is there, rho of liquid and rho of vapors, there is a vast difference. For water, you can say the density is 1000 kgs per hour, and for steam the density is say 1 or 2 kgs per meter cube. So when you subtract this, your value of density for liquid, that is almost negligible. This value of rho L minus rho V, that becomes a negligible change, and it can be taken as rho square. So you have to don't get confused with the other book numericals or other book derivations. There, this rho square, that can be modified with the rho L into bracket rho L minus rho V. This change you can observe in few books.